In this lesson, we are going into a new chapter that is rigid body planar kinetics. But before we begin with planar kinetics, I'm gonna talk about the mass moment of inertia. So basically, mass moment of inertia has been covered in statics. So we are just gonna briefly go into this topic just to refresh the memory on what you have already learned in statics. So what does inertia means? Inertia is basically the resistance of an object to change its state of motion. The most familiar physical quantity of inertia is mass. For example, let's look at the man here that is trying to push a car. So he is giving a force of F to the car, and the mass of the car, M2, is the one that is resisting the motion of the car because its current state of motion is static. So from the Newton's second law of motion that states that F is equal to ma, when we rearrange this equation, we will get A is equal to F over m. So A is the motion of the car, F is the force exerted on the car. Therefore, this shows that the force F that causes the translational motion, the mass m is the one that is resisting the translational motion. So in this case, the mass m down here is the inertia of this car, of the rigid body. What about rotational motion? What causes rotational motion? If in translational motion, the force is the one that causes the translational motion, in rotational motion, it is the moment of force. The moment m here is calculated by multiplying the force applied with the distance d. That is known as the moment of force. So what is the equation of motion for rotational motion? It is given by this equation, mg, that is the moment of force about the center of gravity g, is equal to ig times alpha. Alpha is a familiar quantity. We have already found alpha in the previous chapter, kinematics. Alpha is the angular acceleration or the rotational acceleration of a body. Ig in this case is known as the mass moment of inertia of the body. So if we rearrange this equation here like what we have done for translational motion, we will see that the angular acceleration alpha is equal to mg divided by ig. Like what we have previously, A is equal to F over m. So in this case, mg is the one that is causing the rotational motion, and ig down here is the one that is resisting the motion. So in this case, the inertia of a rotational motion is indeed the mass moment of inertia ig. This is the quantity that is resisting the rotational motion. So from statics, you have already learned that the mass moment of inertia is given by this. This is how the mass moment of inertia of a body is derived. So let's say we have a rigid body like this, the blue color rigid body, and we have an axis z passing through the rigid body like this, and the mass moment of inertia about z-axis izz is given by the integration of r square dm, where dm is the change of mass that is equal to the density of the rigid body multiplied with the change of volume. But in dynamics, we are not going to emphasize on calculating the mass moment of inertia, but whenever there is a problem that involves mass moment of inertia, you will be given this standards formula to calculate the mass moment of inertia for homogeneous solids. So say that the problem involves homogeneous solids. So these are the list of mass moment of inertia that has to be used to solve the problem. For example, if we have a sphere and you see that there are multiple axes here, x-axis, z, and also y-axis. So the mass moment of inertia about x, y, and z is equal. That is equal to 2/5 mr square. For a thin circular disk, you see that the mass moment of inertia about x-axis is equal to the mass moment of inertia about y-axis, that is 1/4 mr square. But if you calculate the mass moment of inertia about z-axis, it is 1/2 mr square. And let's say we have another axis over here, z prime. This is equal to 3/2 mr square. This the mass moment of inertia about an axis that is not passing through the center of gravity of the solid can be calculated using what we call as parallel axis theorem. So normally the mass moment of inertia is calculated about an axis passing through the center of gravity. Now if we want to somehow calculate the mass moment of inertia about an axis that passing through point P over here, which is not passing through the center of gravity, then we have to use what is known as the parallel axis theorem. The parallel axis theorem is given by this equation here, I of z prime, in this case, is equal to Ig, which means that Ig here is I about ZZ that passing through point G, plus M, which is the mass of the rigid body, and D square here is the distance between the axis that passes through point G and axis that we are calculating the mass moment of inertia about now. So basically D in this case is the distance between Z and Z prime. So this should be the distance of D. So in this case, Ig about Z-axis is given by, from our previous slides, it is 1/2 mr square plus M. And in this case, the distance between Z and Z prime is indeed the radius of this thin disk. So it is equal to R, therefore R square. So half mr square plus mr square, we have 3/2 mr square for the mass moment of inertia about Z prime axis. And what if the rigid body given is not homogeneous? Not all the time we are calculating the problem involving homogeneous solid. So in the case that the rigid body is not homogeneous, then we cannot use this formula to calculate, because this formula only applies for homogeneous solids. So in the case if we have a problem involving non-homogeneous solids, then normally another quantity will be given that is known as the radius of gyration. The radius of gyration is given by K, that is equal to square root of I over M, which has a unit of meter. So the radius of gyration, from the radius of gyration given, we can determine what is the value of the mass moment of inertia. So normally the radius of gyration is given and the mass moment of inertia is determined by this equation I equals to mk squared, because k is equal to square root of I over m. So that is just a brief introduction about the mass moment of inertia. In this lesson, we are going to discuss about the first chapter of planar kinetics of rigid body, that is the force and acceleration, and we are talking about the translational type of motion. So previously in statics, we have been talking about the force exerted on a body and also the moments. And from statics, we know that the equation or the summation of forces is equal to 0. And so does the moment. So if we look at the two-dimensional problem, like the planar problem that we are discussing in this chapter, then we can say that sum of all forces in x-axis is equal to 0, sum of all forces in y-axis is equal to 0, and also sum of the moments about point P, for example, is also equal to 0. This is what you have learned in statics. That is why it is static, because everything is equal to 0. Now, this is not the case for dynamics. In dynamics, the forces now is not equal to 0 because the rigid body is now in motion. So in this particular chapter, we are talking about the Newton's second law of motion, that is F equals to ma. So the summation of forces is now equal to the mass of the rigid body multiplied with its acceleration in x-axis and also y-axis. And if the rigid body is undergoing rotation, then we have the summation of moment that is equal to Ig times alpha that we have just discussed in the mass moment of inertia just now. Now let's take a look at the free body diagram and also kinetic diagram. Before we begin with any calculations in this planar kinetics chapter, it is required for us to draw the free body diagram and also the kinetic diagram. This will help us when we perform the calculation in this chapter. So what is the difference between the free body diagram and the kinetic diagram? The free body diagram is drawn to identify external forces that are currently acting on the rigid body, whereby the kinetic diagram is a diagram that shows the effect of the acceleration component ma on the object. So let's take a look at an example. Let's say we have this example here. The 50 kg crate, the box here, rests on a horizontal plane for which the coefficient of friction is mu k equals to 0.3. The crate is subjected to a towing force of 400 Newton, moves to the right without tipping over. Draw the free body and kinetic diagrams of the crate. So how do we begin by drawing the free body diagram? So we draw the same box to represent the crate. We start with the free body diagram first. And whenever there is a body, definitely it has a mass. Then when it has a mass, there will be definitely a weight force pointing down. So this is the first force that is currently acting on this rigid body. So we have the weight force. Weight is equal to m times g, the mass times the gravitational acceleration g. And then since the rigid body is resting on a horizontal plane, so it is basically in contact with the surface down here, there will be a normal force pointing up. So we have a weight pointing down, normal force pointing up. This is in y-axis. And we have a towing force P here. So this is another force that is currently acting on the crate, on the rigid body. And finally, it says that this is moving on a rough surface that has a coefficient of friction mu k is equal to 0.3. So therefore, we also have a friction force. Friction force is always pointing in the opposite direction of the direction of the box, of the crate that it's currently traveling. So the crate is traveling to the right, therefore the friction force is pointing in the opposite direction, that is to the left, and the friction force Fr is equal to mu, the coefficient of friction, multiply with the normal force N. So Fr is equal to mu N. So this completes the free body diagram of this problem. In statics, there is just the free body diagram. But in dynamics, this rigid body here, the crate is moving. Therefore, we need another diagram that is known as the kinetic diagram to show the effect of the acceleration component ma. Because in dynamics, F is equal to ma, and the sum of F is not equal to 0. So to draw kinetic diagram, we draw the same box, the same rigid body. And let's look at the motion of the crate here. The crate is not moving up and down in the y-axis. The crate only moves to the right in the x-axis. So in our kinetic diagram, we draw an arrow pointing to the right, and we say that this is m times a of x, which is denoting the acceleration component ma, because the acceleration component ma is not present in y-axis. We only have the a component, the acceleration component, in x-axis. And this completes our kinetic diagram. Let's now take a look at this example here. We have a trolley with a towing force P pointing in this direction. This is the center of gravity, and we have two wheels both touching the ground. Okay, and probably we can let's assume that the surface is smooth. So in this case, when we draw the free body diagram, we draw the weight pointing at the center of gravity. So we have 60. This is the mass of the trolley here. Multiply with G, 9.81, and we have two wheels at point A and B. Therefore, we have the normal force at point A and and also normal force at point B and B. And we have this towing force P of 300 Newton in this direction. And here, A here denotes the kinetic diagram. This is the direction that the trolley is traveling. Same example here. We can draw the free body diagram and also kinetic diagram. Basically, we're going to have a weight pointing down. 150 is the mass of the trolley. Multiply with G, 9.81. At point A and point B, we have the normal force because both points are in contact with the ground. And we have the towing force P that is applied to the trolley. P is pointing to the right. And here is our kinetic diagram. The trolley is not moving in y direction. It only moves in x direction. So we have here the component of max. M here has been substituted with 150. That is the mass of the trolley. And it is multiplied with A. So these are two diagrams that you must draw in order for you to solve the problem in this particular chapter. So let's look at the general equation. Say we have this rigid bodies here. We have this rigid body like this. There are a few forces and moments acting on this rigid body, and there is the weight force pointing at the center of gravity. And for translational case, the kinetic diagram can only have two arrows. It is either moving in x direction. It can also move in y direction, or it can also move in both direction. If the rigid body is, let's say, traveling at an angle in this direction, for example, so we have two components of MA, MAX, and also MAY. So the basic equation is from all of the forces and moments that are acting on this rigid body for translational motion, we have the sum of F in x direction is equal to magx. The sum of F in y direction is equal to magy, and the sum of all moments is equal to 0 because the rigid body is not rotating. Remember, we are talking about translational motion in this case. Therefore, the sum of mg is indeed equal to 0 because the rigid body does not rotate. And remember that we also have a curvilinear translation. So in the case of curvilinear translation, normally we change the axis. We no longer calculate the sum of force in x-axis, but we now calculate the sum of force in n-axis, the normal axis. The normal axis is always pointing to the center of rotation. So the sum of Fn is equal to magn, the acceleration in the n-axis, in the normal axis. And also we have the sum of Ft, sum of forces in the tangential axis, that is equal to mag-t. Tangential axis is always tangent to the path of the motion. So from our kinematics chapter, we know that an is equal to omega square times r, and at is equal to alpha times r. So this equation now becomes Fn equals to m omega square r, and Ft equals to m alpha r. Now let's take a look at an example here. So we have a car that has a mass of 2000 kg and a center of mass at point G. Determine the acceleration of the rear driving wheels that are always slipping. What does this mean is that the rear wheel here is influenced by the friction. That is why it says always slipping. Whereas the front wheels are free to rotate. Free to rotate here means that the front wheel of the car is not influenced by friction. Neglect the mass of the wheels. The coefficient of kinetic friction between the wheels and the road is mu equals to 0.25. So remember, the first step when we are calculating kinetics problem is to draw the free body diagram. So in this case, when we draw a free body diagram, we have a weight pointing at point G, pointing down. This is 2000, the mass, multiply with 9.81. This is the gravitational acceleration G. And we have point A and point B that is in contact with the ground. Therefore, we have the normal force. Whenever there is a contact between a rigid body and the ground, there will be normal force acting on that contact point. So we have normal force at point A and also normal force at point B. Now it says that the driving wheels, the rear wheels are always slipping, so we have the influence of friction here. And you see that the car is moving moving to the left, but the friction is also pointing to the left. This is because of the rotation of the wheel. If you see, when the car is moving to the left, the wheel rotates in counterclockwise. So the rotation in counterclockwise will result in friction to oppose the counterclockwise rotation. The rotation is like this. So to oppose the counterclockwise rotation of the wheel, therefore the friction is also pointing to the left. The direction that you point the friction force here does not really matter, because if you point the friction to the right, then in the end, in your calculation, you will get negative value, which means that the direction is actually pointing in the opposite direction. So this completes the free body diagram of the car. So we have in total 4 external forces acting on the car. Remember, apart from free body diagram, you also need to draw the kinetic diagram. So in this case, the car is not moving up and down. the car is moving to the left. So the kinetic diagram will be from point G pointing to the left, and this will be magx, or you simply write down 2000 for the mass times ag, the acceleration of the center of gravity. So how do we proceed with the calculation? This is our free body diagram just now. Remember that we have three equations: the summation of force in x-axis, the sum of force in y-axis, and also the sum of moment. So for translational motion, we have sum of force in x-axis that is equal to m times agx. So let's look at the forces in x-axis. Remember, we set our coordinate system to be in this direction, x positive to the right, y positive going up. So in this case, we have a friction force that is pointing to the left, that is equal to 0.25 Nb. So in this case, because it is pointing to the left, it becomes negative. So on the Fx side, on the left hand side, we have minus 0.25 Nb equal to magx. So we have ag in the x-axis, so also pointing to the left, therefore it is also negative, so minus 2000 ag. That is our first equation. Now let's look at the sum of forces in y-axis. So we have Na pointing up, positive, Nb pointing up, positive, and the weight pointing down, negative. So Na plus Nb minus 2000 times 9.81. That is the sum of forces in y-axis, the left-hand side of the equation, equal to magy. If we look at our kinetic diagram, there is no motion in y-axis, therefore this is equal to 0. That is why the free body diagram and the kinetic diagram is very important to solve this problem. Therefore, by looking at these two diagrams, the free body diagram and the kinetic diagram, you can easily fill in what is what should you write on the left hand side of the equation and also on the right hand side of the equation. So you have Na plus Nb minus 2000 times 9.81 equals to 0. That is our second equation. We have the third equation, which is the sum of moment. So the sum of moment for translation is equal to 0 because the car is not rotating. So when you sum moment about center of gravity G, remember that moment is force multiplied with distance. So, and we always take counterclockwise as positive, remember. So for Na here, Na is in this direction. To go to G, it will be rotating like this. So to go to G, it will have a rotation in this direction. Okay, so this will be negative because it is clockwise. Therefore, we have minus Na times 1.25. This is the distance between Na and point G, because we are now calculating the moment about point G. So everything has to be referred to point G. Let's look at the weight. The weight acts exactly at point G. Therefore, there is no distance between this force and point G. Therefore, there is no moment of the weight at point G because there is no distance. Distance is simply 0. Moment m is equal to force F times distance d. So when d is equal to 0, therefore the moment of the weight about point G is also 0. Next is NB. Point B and B here is 0.3 multiply with 0.3. Sorry, this is 0.25 NB. This represents the FB here. FB is 0.25 NB. So this is pointing in this direction to go to point G. So you see that this rotation is also clockwise, therefore it is negative, okay, because of clockwise direction. So minus 0.25 NB times the distance is here. This is the distance, 0.3. So multiply with 0.3. And finally we have NB, that is now to go to point G is rotating in counterclockwise. Therefore NB, moment of NB is positive. So plus NB times 0.75, which is this distance from NB to point G. And everything is equal to 0 because there is no rotation of the rigid body. So in the end, we can then solve this equation. We have minus 0.25 NB equal to minus 2000 AG. We have NA plus NB equals to 2000 times 9.81. And we have this equation as well. So we can solve these three equations to finally get AG is equal to 1.59 meter per second square pointing to the left. NA is 6.88 kilonewton and NB is 12.7 kilonewton.